the curse of dimensionality. And so that's one reason why we might want to reduce these number of dimensions. So I'm literally just talking about, like, we've got a data set that's got like 10 columns in it, and we want to get those 10 columns down to 3 columns. That's what we mean by reducing the dimensions of our data sets. But we want to do that in a clever way that keeps the most amount of information as possible. And when we talk about information like this, it's basically analogous to variance. So our data points vary from each other, and when we reduce the dimensions, we want to maximize the variance that's still left over, and that keeps the most information still in our data set. So one reason to do it is you could do PCA, reduce your dimensions, and then feed those new dimensions into your machine learning algorithm. That would both reduce the amount of time it takes for the algorithm to run, and in some cases might even boost the accuracy a little bit. Another reason you might want to reduce dimensions like this is to visualize the data. So we can only visualize things like in 1, 2, or 3 dimensions. We can't visualize in 4 dimensions or higher. And realistically, it's hard to make visualizations in 3 dimensions. So a lot of times you can do PCA to get your data set down to 2 dimensions so you can visualize it. And that's what we're going to do a lot of today. So these are some visualizations, and we're going to go a little bit fast through this since we linked those videos and we're trying to get to the work time in the second half of class. So these are some visualizations to kind of help you understand what's happening. If we look at this point cloud here, it's already in 2 dimensions. So we're going to reduce it down to 1 dimension. And if we had to pick 1 dimension to reduce this data set down to, first of all, would you guys pick the X or the Y? Which one has the most variation in the data set? The data along the X-axis horizontally, or the data along the Y-axis vertically? Drop in the chat which you think would be better to reduce it to if we had to pick X or Y. We got a vote for X, got another vote for X. One more for X, that's good enough for me. So yeah, you guys are right. And we can just look, it goes from like, -2.5 to +2.5 on the X. It only goes from -1 to 1 on the Y. So you can just think about it, if we squished everything down to the X, it'll be more spread out than if we squished everything down to the Y. But is there a direction you could pick that would be better than X or Y in this case? Like if you had to pick an angle between 0 and 90 degrees, about what angle would you pick that would maximize the amount of variance if you projected all those points down on that angle? Yeah, exactly. So a 45-degree angle here would capture even more of the variation than just the X or just the Y would. So that's the whole idea here, is that we're trying to find the new axis that'll retain as much of the variation in the data as possible. And so that's a nice little picture in 2 dimensions. And then you have basically an analogous situation when you're in higher dimensions. And we're not going to go into the linear algebra because it's pretty complicated, but that's kind of the basic intuition. So to actually do this, we use the sort of same pattern that we've been using with a lot of our scikit-learn algorithms. So up at the top here, we imported PCA, principal component analysis, from sklearn. And so the same way we initialize a classifier or a regressor, we're just going to initialize our PCA as this scikit-learn PCA. And the important thing that we specify is the number of components. And so we'll dig into more into how you pick this number of components. But right now, we're just going to start with 2. And so we're not actually reducing anything. We have 2 components in our data. I can show you what our data looks like real quick. It's not even in a data frame, but we've got 2 columns here, a 2-dimensional NumPy array. And so by setting our in components 2, we're not actually changing anything. So we initialize it, and then we fit it to our data, just like we do with our machine learning algorithms. And then what it spits out is it'll spit out a component And so this is like, you could think of it as the vector of um, the new like axis. Yeah, a vector showing you the direction of the new axis. Um, so you don't often need to actually go in and look at the components like this. And then the other important thing we get here is the explained variance. And so this is saying out of the total variance, this is how much actual variance is explained by the first component, and this is how much variance is explained by the second component. So you can see the first component here gets a lot of the variance, and then the second component is only adding a tiny bit more. It's actually more helpful, I think, to look at the ratio of explained variance instead of just explained variance. So the first component gets like 98% of the total variance inherent in the data set. And then by adding the second component, we're only getting 2% of the variance. So you can think about it as if we take this point cloud and we project it onto this line at about a 45-degree angle, we'll just have like a number line with a bunch of dots on it, but that number line will have about 90%, 98% of the information that's present in this data set. So that's the idea. To actually show you what's happening, these are our new vectors here. So these would be like our new axes after we transform our data using this PCA. And so now that we fit the data, we have to also transform it. And so normally this is done in one call, you'll see later. Normally you just make a new data set. So here it's called data PCA. And you just do equals, PCA was our object that's holding our algorithm, and you do fit underscore transform on your initial data. And so this will fit the PCA to it. It'll figure out what the new axes should be for the number of components you specified, and it'll reduce your data to the new components and store that over here. Since we already fit it, we just have a transform here. And so if we transform the data and then graph it again, you can see it looks a little bit different, and it's graphed. These X and Y axes have been transformed to be the axes defined by these components up here. So that's the basic idea. Now we're going to do it with just one component instead of two, and we're going to fit it and then transform it. And if we print the regular data shape, we have two columns. If we print the new data shape, we only have one column, but the same number of instances. And then we can graph it. And this orange here is the new data. The blue is the old data, and you can see that it's been projected along this line here. So that's a very quick, very high-level overview of what we're trying to accomplish. Any questions about that so far before we jump into an example of how we actually do it in practice?
I have a quick question about like the transforming the data. If there was like one little dot, let's say it was at, -2, 1.5, would that mess up sort of like the angle that you needed to find to transform it, or not really?
Yeah, that's a good question. Do you guys do the 7 o'clock clap in your neighborhood? Can you hear the people banging on drums and tambourines outside my window? It's a cool thing. So Meldon's question is like, if you have a big outlier, how's that going to affect the components? Honestly, I'm not totally sure. So first of all, it'll still be projected down like everything else. That much is clear. How much it would change the angle? I think it wouldn't change the angle very much. I think PCA is pretty resistant to outliers, but it would definitely change, like have an impact. It would definitely shift it up towards itself a little bit, I think. So that's a good question. And yeah, the basic answer is I don't know. So people talk about algorithms in terms of how resistant they are to outliers. So we can do a quick Google search. Oh, it's sensitive to outliers. Good thing I searched. So yeah, great question, Melvin. So this would be a good thing to read up on. I'll have to read up on this later. So you could drop outliers from your data when you fit the PCA and then still have them in when you transform would be one possibility. Or it looks like people have been working on alterations to PCA to kind of reduce the impact of outliers. a great call out. If you've got some significant outliers in your data, something you should be aware of. Looks like it's not, it looks like it's sensitive to these outliers. That's a good question. Any other questions about the sort of general idea of what we're trying to accomplish here? Cool. So we're going to do an example. Go ahead and open this notebook up if you haven't already. And we're going to do an example on this Wisconsin breast cancer data set. While you guys are opening it up, I'll show us what we've got in here. So we've got an ID column, we've got a diagnosis. One is, so this is all data on cancerous cells taken from breast cancer patients. A diagnosis of 1 means the cancer ended up being malignant. A diagnosis of 0 means the cancer ended up being benign. And then these are all characteristics of the cell. So like the radius of the cell, the smoothness, all these different things. The original data set has like 30 columns. I limited it down to these 10, which were like the 10 in the original data set, 10 plus the ID and diagnosis. So make sure you run this little cell here in your notebook, or you might end up getting some different results. And we're going to have you guys try to fit and transform the PCA. And the object here is to visualize to see if the malignant and the benign cancerous cells, we're going to visualize if they group together separately or based on this data set, or if they're just all mixed up. But to visualize, we first need to reduce these 10 features down to 2 features. So our features, I set it up for us here. Our features are these 10. So it's everything in the data frame except the ID and the diagnosis. So what you need to do is first, I didn't mention this, but it's very important that we scale the data. So that was just in our Kahoot, and we talked about it in the regression lesson too. It's very important to scale the data before feeding it into the PCA, because the PCA is sensitive to the scale of the data. So if one of the axes is on a scale from like 0 to 100 and the rest are on a scale from 0 to 1, the axes on the scale 0 to 100 will dominate everything else. So we need to have everything on the same scale before we feed it into the PCA algorithm. So what you're going to need to do is initialize your standard scalar, use the scalar to fit and transform your features, initialize your PCA with 2 components, use the PCA to fit and transform your features, and then I wrote the code at the end here to put everything back into a data frame, so you don't need to do that. So go ahead and try that out for about 5 minutes or so. After a couple minutes, I'll start filling in my version here so that we can see how it's done. All right. Anybody hitting any problems yet? I'll do the standard scalar part. So all we need to do is initialize the standard scalar like that. And then we're going to do scalar dot, we can do the fit and transform step in one, and we're just calling it on the features. So we initialize it, our features have been set. We don't want like the ID and the diagnosis in here, so it's the data frame limited to these. And then we reset that same variable features to be the fit transformed versions of the feature in the scalar. And we're going to do basically the same thing we just did, but for PCA, initialize our PCA. We want the number of components to be 2 because we are planning on graphing it in 2 dimensions. And then our features will just be PCA.fit transform. Oops, our features. Cool. Think that should work. Seems like it worked. So in this last line here, I made a new data frame, our PCA data frame, and I didn't want to lose our ID and diagnosis. So I put together the ID and diagnosis from our data frame and our features. So our features came in labeled component 1 and component 2. And we have our ID and diagnosis here. And then now we can plot. So what's happening in this plot, this is up here, just kind of all stuff we covered in our lesson on plotting. And then we're just doing a scatter plot. We do it 2 different times. Once with the color red, only those rows of the data frame that have a diagnosis equal to 1. And we're graphing the component 1 and the component 2. And then in green, the benign equal to 0, we're graphing component 1 and component 2. And if we look at it, so this is telling us that we should be able to successfully classify at least most of these cells, because we've got a pretty clear separation right in here between the red malignant, I think, the red malignant cells and the green benign cells. And so it's not a perfect separation. There's quite a bit of overlap here. But hopefully this seems at least somewhat cool to you guys, that we were able to take our 10-dimensional data set that we wouldn't be able to visualize and see the separation here. Maybe to kind of illustrate what's happening here, let's try visualizing. We're going to do the same thing, but instead of visualizing our components here, let's just pick. So we're going to use our regular data frame, and let's just pick like the first 2 features here and see how much that's separated. So we've got texture mean and perimeter mean. So I have no idea how this is going to turn out. Maybe I'll end up eating my words and it'll look exactly the same or something. But hopefully it looks significantly different and you're able to see the value of the PCA here. So we're doing the same thing. Yeah, exactly. The principal components is a combination of all the features. That's a good question, Tyron. So what's happening kind of under the hood is it's figuring out, this is just an example, but maybe it's taking the first 5 components and it's like, okay, I'm going to mix together, like the mix that maximizes the variance is going to be like half of component 1 plus 1/8 of component 2 plus a little bit of component 3. And it turns out, or sorry, like feature 1, feature 2, feature 3, and it turns out the feature 4 and 5 don't matter, and I'm going to put those together into my first component. And then component 2 is going to be, you know, like a little bit of feature 6, a little bit of feature 7, feature 8 and 9 don't matter, and then a little bit of feature 10, and those get mixed together into component 2. So these component 1 and component 2 are a mix of all the features, but they should do a better job of separating the data than just 2 random features here. Let's see if that's actually true. This actually did a pretty good job. So you can see it is different. We've split left, right instead of up, down. But it looks like if we just kind of pick some of these features, that still kind of works. So that's interesting too. Let's try some of these other ones. I'm just kind of interested now. Let's try concavity. Multifractal dimension, because that one sounds cool. Well, this one works pretty well too. So that is a little bit worse than our principal components. We've got some greens way over here, and this looks a little bit more mixed up to me than it did up above. But that's the idea, is that the principal component's gonna find the best two components, and it's not just picking two, it's doing a mix like Tyron just said, but it's gonna find the best mix to maximize the variance here. So the very last thing on principal components is that in that last example, when we're trying to visualize, we'll pick two. But if we're using PCA to just like reduce the dimensions to feed into another algorithm, how do we know how many components we want to fit? So like in this example, we've got 10. So any choice from 1 to 9 would reduce the number of dimensions. How do we know which number is the best one? And we know basically the basic idea is that we want to find the number where we start hitting diminishing returns. And we do that by looking at the explained variance ratio. So if we fit a PCA here with 10 components and then look at the explained ratio of those 10 components, the second one here is the cumulative sum. So with one component, we get 55% of the information. With two components, we get 80% of the information. 3 is 89, 4 is 94, 5 is 97. And then after 5, it goes like 97, 98, 99, 99, 99. So there's not really any reason to do like a 7, an 8, or a 9. Because you're not really adding anything with a 7, an 8, or a 9 that you're not getting out of a 6. And you're really not even getting anything out of a 6 that you're not getting out of a 5. So if you're not doing 1 or 2, 3, 4, and 5 will all be reasonable choices. But anything above 5, you start to hit diminishing returns. So that's the basic idea, is you want to find out how many components you need to get a good amount of the variance. And then after that, you can forget about the rest. And so you can look at it like this, but there's a fun technique called the elbow technique. Oh, wait, where'd my elbow go? Oh, I guess I didn't talk about the elbow till the clustering. So you can just look at it and see, and I chose 5 here, and we'll talk about the elbow technique in clustering. That's just the way to visualize where those diminishing returns start happening. Cool. So we're going to transition into clustering, and Carlos is going to take over there. But any questions about principal component analysis before we move on? And yeah, thanks for asking that clarifying question, Tyron. Principal components, it might be an easy mistake to make, to think that it's like just picking the best 2 of the features, but it's actually totally recombining all of the features. All right, questions going once, going twice. Otherwise, let me stop sharing and we'll have Carlos tell us about clustering.
Okay, can you guys see the notebook?
Yep.
All right, cool. Okay, so there's one last thing I want to cover. As Steve was explaining about the spleen variance ratio. And hold on. Let me do something quick here.
Oh, I thought that I had a plot. Yeah. So thanks for putting that plot PCA in there. I was wondering why it wasn't showing up.
So let's say if you want, you can use this function here. Let me show you this one. Yeah, the plot PCA. So for the plot PCA, what you can do, like here, I filter the columns that I want to check, and here I standardize the actual data frame, and here you specify the names of the columns, and then when you run it, so what I did, I have the bars to explain how much each bar has as a spleen variance, and the blue line here represents the cumulative spleen variance. And one good point that Steve explained like 2 minutes ago is that if you choose, let's say, 1, 2, 3, 4, like basically only 4 columns explain 90% of the whole data. So you don't have to use all the columns in the data set. Again, like here, like you can use the radius mean, tester mean, perimeter mean, and the area mean, and yeah, that's basically going to give you like over 90% of information. Yeah, so now, do you have any? Are there any questions? No questions. Let me open the chat just in case. Okay, so let me continue then. So now we can move on to clustering. So clustering is when, can someone tell me what clustering means? At least if it does sound any alarms to you, like, where's the
putting stuff together with commonalities.
Yeah, that's good. So basically it's like doing classification, but you don't really know what you actually classifying. So yeah, basically you're grouping everything based on what they have in common. Good answer. That was who was this?
On voice?
Yeah,
Shizoda.
thank you. All right, so cluster. So there are a few algorithms that you can use for clustering. One of the most famous algorithms is called KMeans. And what KMeans does is that he looks for the centroid of a cluster. Like, let's say he looks for the point that is exactly in the middle of the cluster. And basically what it does is that it picks a point and then it goes measures the distance to every point. And it decides to what cluster a point belongs to based on that distance. Let's say, for example, here we can generate data using the make blobs from Sklearn. As you see here, you have 4 clusters, obviously, but you don't know what it is. Now the question is, how can you create labels for these clusters? And you can use the k-means, and you specify the number of clusters you want. You say, oh, I want 4 clusters. So what you do is that you feed the data, which in this case is X, the data we don't know, and then you can predict the label of that data using the predict method from k-means. So if we do that, when we run it, and now let's see the color that each cluster has. So as you see here, every cluster has their own color, and the dark circle you see here, that's the centroid of each cluster. As I said, the centroid is the point that is the actual center of the whole cluster. It's that member that basically is like that member that represents the cluster. Do you guys have any questions? Any questions about K-means and the centroid? Or maybe, quick question. How do you guys think that the centroid measures the distance to every point? Like what kind of distance it measures?
Euclidean.
Yeah, that's right. It's the Euclidean distance. Like, you can say Pythagoras. So now, one of the problems with K-means is that you have to specify the number of clusters you want. And sometimes you don't know that. So there is a technique for that to determine which is the best number of clusters based on the data you have. So let's say, for example, here, if instead of 4, we specify 6 clusters. When we run it, you see you have these 2 clusters here and these 2, which in a sense they're very close together. Oh, I didn't see this part of the chat from Julio that says Euclidean distance, Manhattan distance. Actually, you can specify one or the other. You can say if you go to K-means, and ask the question, is it per compute distance? And check here, it says per compute distance. Hold on. All right, so I'll owe this one to you guys. But yeah, let's continue here. As I said before, like when you don't know the number of clusters, so we were here, 6 clusters. Yep. And it's not something that like you basically it's not like a trial and error problem. So you have to like set up a for loop and see how the matrix that you want, that basically tells you how many which number of clusters are good. Let's say, for example, here, if we say, oh, we want only 3 clusters. Can you guys see the problem here? Who wants to volunteer and see and tell me what the problem is here compared to the other 2 examples using K-means? Yep. Anyone? Come on, guys. Do you guys see any problem here in this graph? Like compared to okay, not enough clusters. That's good. And what else? Let's say this cluster here. Okay, why it should be 2?
It just looks like it should be 2. They're like there's 2 separate groupings.
Yeah, and you see the centroid is right in between the 2 clusters.
Right.
Yeah. So this technique called the elbow method, and you're going to see why they call it the elbow method. And what it does is that it gets the what is called the inertia of the model based on the number of clusters you get. And the idea is to have the lowest inertia point. I mean, not the lowest, because sometimes it can go wrong to have many clusters. But like when you run it, you see here, like for I have the clusters from 1 to 9, and I fit the edge, and every time it's fitted, I get the inertia based on the number of clusters. So when I run it, and here on the edge, you have the number of clusters you want, which is the K, and the inertia. So the idea is to have the lowest inertia. And can someone tell me here from the number of clusters, which one could be a good number? From 1 to 9, if you have to pick one, which one?
4.
Why 4?
you're not getting much of a difference from going from 4 to 5 to 6.
Good. So basically it starts converging, right? It's like a plateau, kind of. So that's good. And that's why it's called the Elbot method. You see, it looks like a horn. It looks like an arm, kind of bended. So this is the point one. The let's say the like the inflection point. And let's say we can have another problem that you have like a higher order combination. So in this case, the model itself is not going to be that efficient to determine which cluster is what. So one technique that you guys can do is use PCA and transform the features. So there is one PCA. There's something called the kernel trick, and I'll show you how to do it now. So the kernel trick, you can do it using the kernel PCA. Say we learn the composition, import kernel PCA. So what can you do with kernel PCA? This is what we can do with kernel PCA. Hold on. Let me make sure first I have the right name. Kernel. Okay. This is what I want, the RBF. So the kernel RBF, what it does is that it basically it combines the all the features. And so let me take two components. What it does is that it combines all the features into higher space. So basically it creates all the features with the features that you already include, and then take the best features overall. So let's see how this changes compared to this one here. So we can say X is equal. Okay, let's see now. All right, let me take this code here. All right. You guys see?
Dope.
Do you guys see any difference now, like compared to this one? Any questions? Come on, guys. No questions? Oh, man. Okay. So let's continue here. Solution. Sklearn has a model built for this. Yeah. So let's run this part. Okay, I think this is for you to work on. So that way you can run it and play with it. So how many minutes, Steve?
I think they could do this one, or they could do the iris one at the end. I think the iris one would be a little bit better. This breast cancer one is an example of like doing the elbow method to see how many. So if you scroll down a little bit there, you'll see the elbow, and we can see that 2 is like the good elbow. Oh, you passed it. There you go. Although interesting, you could make an argument for like 3 or 4 too. But yeah, let's have them work on the iris one at the end, and that'll be a good chance to practice both PCA and clustering at the same time.
Okay.
So the iris is another famous example, famous machine learning data set. And so we've outlined it a little bit for you there. So you already have code that reads in the CSV, and then you have code that tells you what the features are. And so you're going to need to scale the features, make the PCA, and then transform the features with the PCA. And then we even included the code that will visualize it too. So that's the PCA part, and then after you do the PCA, you can do the elbow method to see how many clusters you could do, and then make clusters on that iris data set. So let's take like 10 or 15 minutes to do that. We can come back together and do it together, but take the notebook and see if you can apply what we've just been talking about to this iris data set at the end of the notebook here. Maybe post the visualizations you get in the Slack and let us know if you've got any questions.
You guys want me to continue this part, or I'm sorry.
You've got your screen share up there, Carlos.
Okay. Thank you, man.
We're gonna talk about you guys on Slack. I don't think we need to run through this breast cancer here. It's just another example where, and it's kind of typed up in the notebook there, so we can jump to the example.
Yeah, it can go lower. It can. So you think, I don't know, maybe some of the students want to share what they have done?
Is that notebook working for you guys? Is anybody having problems trying to do their own PCA on the iris data set? Are you guys chugging away? We can't tell because we can't see you, so it makes our job hard. Great, thank you, Ty. All right, we'll give you guys 10 minutes or so to work on it, and we can start to do it piece by piece as we're waiting here. We'll take the scaling, should be fast, so we'll do the scaling. I'll throw up my solution in just a second. And if you want the visualization to work, pay attention to my variable names there. So iris underscore features is what I try to visualize at the end. So here's the scalar part. We've done that a bunch. Hopefully that looks familiar. We've got scalar equals standard scalar. Iris features equals scalar.fit transform on itself, iris features. All right, hopefully you guys are making some progress. Put the PCA. I guess I didn't follow my own comments here. Put the PCA in my code as well, so this should run and visualize now. Oh, it did not. Where is my error? Oh, I didn't actually load my data frame. Nope, still a problem. So I should have included this code for you guys, but once you make the feature, here's someone cooking in the background. once you make the features, you got to make a data frame with the features in it to get it to actually visualize, right? I should have come up with a way to fix that. Let's see if this works. There we go. So we've got our standard scalar. We've got PCA and components equals 2. PCA fit transform on our iris features. And then the way I set up the visualization down here, we put our features back into a data frame with column names equal to component underscore 1 and component underscore 2. And in this part then should work to put it into a big data frame with the labels and then graph it for us. So we can see we've got one really clear cluster, and then these are the actual names. These aren't the cluster we've generated yet. That's in the next step. And they are separated, but they also intermix a bit. So it'll be interesting to see how the cluster algorithm handles this. It should definitely pick up on these red ones, but these green and blue ones might be a little bit harder. Were people able to do the PCA, or people on the cluster section now? Yeah, sorry about that, Tyron. I thought I had set it up for you guys, but I might have accidentally deleted some of the code. I didn't mean to. Did you see how to fix it? Here, I'll share my screen again since this part's a little bit not quite what we covered in the lesson. So this is the line that'll fix the error, putting the features back into a data frame and naming the columns component 1 and component 2. Alrighty, how are we doing on this second half, generating the elbow graph and making some clusters? Still working on that, Tyron, or were you able to get it? Cool. Take a couple more minutes there. Yep. Was that the right section? Is that the section you meant, Shizota, or did you have another section you needed to see? Okay, cool. Cool, Tyron, did you get a elbow graph that looked like the one that was here? Cool. And this elbow graph isn't perfect. I think if like you just showed this to me and asked me how many clusters you should do, I would say 2, whereas we have 3 in the data set. So just there's a bunch of other methods you can use for finding an optimal K. The elbow one's just one of the more intuitive ones. But yeah, shows that it's not perfect in picking these numbers here. We'll give you guys, well, we're gonna take a break until 8 o'clock now. If you're still working on getting these clusters together, or if you want to, like, I didn't put a visualization of the actual clusters on the end here, so if you feel inspired to make a visualization, maybe with 2 clusters or with 4 or 5 clusters to see what happens, I'll stick around to help you out. But yeah, let's take a break until 8 o'clock, and then we're going to come back at 8 o'clock and transition to working on our project. So I'll stick around for a couple minutes if you still have questions, but otherwise, we'll see you guys at 8. Carlos, that kernel trick blew my mind. Oh, here, I'll fill this in for you guys. So initialize with K clusters. Fit to the features. And the inertia to the sum. I don't know, I need to figure out how to get my tab, there we go, to work better in Jupyter Notebook. Dot append.
Oh, I think you need the underscore.
Oh, you're totally right, thank you. Oh, I also need to spell it right. Cool. It's got like a double elbow. Maybe they broke their arm. Feel funny.
I mean, they're not supposed to, because they're supposed to go out now.
Let me see if I can modify this really quick to show our clusters.
So looking at that elbow graph, what would the K be? 3, 4?
Well, that's what I was saying. We know that it's 3, right? But let's pretend that we didn't have labels on this data set. I think you could make a strong case for 2 or 3. And I think if you showed me this, I would probably pick 2. So just one of those things where there's not a perfect method for picking the optimal K. And the elbow method might not even be the best. There's a whole bunch of papers on all sorts of methods and different metrics to look at and things like that. So there's probably like 30 different of them. I was hoping to find a package maybe I need to look harder. I'm surprised nobody's done this, that just does a bunch of these methods for you and then comes back and tells you what like the most common answer was across those methods or something. But yeah, there's no like super clear. Is there, Tyron? Do you know what the name of it is? But there's not a super like clear scientific way to pick. Saw it on LinkedIn. Cool. Well, if you see it again, let me know. I'd be interested to know what it is.
Also, I think there is another algorithm for clustering, and it's called DB scan.
It's called what?
Let me see if I get DB scan. I'll send you the link. I mean, the scikit-learn link to everyone. So yeah, and in this one they use the distance, like the Euclidean distance or the Manhattan distance.
I have seen this one before. This is a good one.
So the DB scan, what it does is that instead of using the centroid as KMeans, what it does is that it looks for the denser regions. Okay.
Oh, sweet. Thanks, Ty. I'll have to check this out.
Thank you, Taran. This looks pretty neat, man.
So as we're coming back, here's a quick visualization. So I did a standard scalar. I did k-means equals 3. So if you do k-means equals 2, it's pretty obvious you'll get this red is one cluster and then the rest of it is the other cluster. If you do k-means equals 3, you fit it, you predict on the features to get the clusters, and then you do a PCA after the k-means so that you're able to visualize the clusters you just got. You can see that you get your obvious cluster and then it kind of splits it top and bottom. But you can see it doesn't actually do a very good job because it's actually almost split more left right here. Like it splits it right around 0, but there's a whole lot of blues. Like all of these blues are getting misclassified and all of these greens are getting misclassified. So that's what happens sometimes. It's not perfect. Now I want to see what happens if we do 4. Oh, I didn't give it another color though. So if we do 4, it actually splits a good cluster twice. So yeah, a couple visualizations there, fun stuff. Any questions about the material we covered today?
My guy.
Questions. Guess we're good. All right, cool. So we're going to try to use the last hour of class as some work time on the projects. Like I said, exactly how we structure this work time is a little bit of an experiment. So we'll see how it goes and we'll adjust for next time. But the idea is that we'll split up into 2 groups, one with me and one with Carlos. And then, so I'll post the Hangouts link in the Slack here in a second. And if you're in my group, you'll click that. And if you're on Carlos's group, you can just stay on this call. But before we split up, we wanted to have you guys just talk for a minute or 2. You can even share your screen and show off some code if you'd like. But just hop off mic and tell us what you and your partner, tell us about the data set that you've picked. Tell us about any exploratory analysis you've done so far to see what's in there. And then tell us what you're hoping the sort of final project that'll come out of it'll be. And if you have a GitHub and you haven't posted it in that Slack thread yet, go ahead and do that. So I'm going to start with the students that replied to that thread. And sorry, you were the fastest, so you got to go first. But sorry, are you there? Have you come back from the break?
Yeah, I'm here.
Sweet. So what's the data set that you're working on, and what have you done so far, and what are you hoping to do over the next couple weeks?
So,
oh, sorry, and who's your partner as well?
It's Nasan, but we haven't done anything for the past week because it's Passover.
Cool.
Let me look at my data set. So we chose to use New York City census. We don't really know where we're going to do. We're thinking maybe try to predict income based on demographics. So sorry, what?
I just said that's a good idea.
Yeah, so I started to do the EDA. We didn't get very far. I started to try and analyze in the different bureaus, how many people work at home, and that's pretty much where we stopped. I noticed that like in Staten Island, almost no one works from home. So I was thinking maybe try and focus on a specific bureau and then look at that bureau data. But I don't know if that's the right direction. So I'm waiting to hear what Nasan has to say once the holiday's over. And that's where we're at.
Great. Thanks for the update. Who else posted in that thread? Tanya. And Tanya, who is your partner? I have Hui Lin, is that right? Tanya or Hui Lin, are you guys out there? We can come back to you. Oh, here we are.
So my partner is Tanya. So our data set is based on the internet usage worldwide, starting from the oldest year, which is 2007, and then to the newest year. So we're just trying to figure out whether, like, if the internet usage has been increasing or decreasing over the past few years. And so far, what we have seen so far, it's been increasing. And right now, we're just trying to improve on the visualizations.
Cool. So are you hoping at the end of it that you'll have some visualizations? Is that the idea?
Yes.
And is there any specific part of the data set that you're wanting to visualize? Is it going to be like a map per country, or is it going to be like an animated visualization over time, or have you thought that far ahead?
We haven't really thought that far yet.
Okay, cool. That's good. Sweet. So hey, Lynn and Tanya working on some internet usage. Love it. Shizoda, who's your partner?
I work with Julio.
Julio. So Shizoda and Julio, what are you guys? Tell us about your data set and what you've done and what you're hoping to do.
Yeah, we're looking at the best borough, and we looked at the total arrests per borough. We looked at like which borough is most accessible by train station. We started looking at which borough also has like the most health inspection violations, and overall which borough is the most diverse. And those are some data sets we've already looked at. Yeah, we'll keep digging around, and just we might shift from getting the best borough to making it just like a fun quiz about the 5 boroughs and getting people to test, like, you know, which borough has the most trees or which borough is the most diverse, and it might just be a quiz, or we might do something completely different. We're just poking around at this point.
Cool, sounds good. You could make a visualization that lets people kind of explore for themselves some of the characteristics that you just listed. I like the quiz idea too. That would be super fun. Sounds good. And so Gurjeet, who is Gurjeet's partner? Meldon, is that right?
Yeah. Me and Gurjeet are partners. We've gathered all the data that we needed. So right now we've just been working on sort of cleaning it up. The way the DOB, or I forgot the website that gave us the data, the way they made it changed up all the columns. So that's really what we're working on now, which is like fixing all the column names for them to be correct. Because right now everything is coming up as unnamed, etc.
Oh, interesting. Okay, I'll look at that with you guys. Maybe there might be an easy way to fix that, but we'll see. And can you tell us what the data is and what you're hoping to, like what you're hoping the final product will be?
Oh yeah, so the data is basically all the homes that have been sold since 2005. And so our end goal hopefully is going to be like a map of the 5 boroughs, and then there'll be a slider, and you'll be able to, you know, see the difference in price per by zip code by borough.
Cool, sounds good. And I accidentally skipped Tyron, I think. Sorry about that, Tyron. Tyron, do you have a partner?
No, I don't.
Okay, cool. Working solo. Are you open to working with a partner if someone still needs a partner?
Sure. I'm still focusing on the TensorFlow with the image classification part for the sign language. But on the side, I'm still working on the GitHub that I posted for the New York police data. I did some like really cool visualization. I use Pandas has this geographical mapping where it maps all the incidents based on the borough. And I also try to do it in Folio. There's some graphics I did, and then I did some data exploration during like crimes during certain times of day, and I was just trying to see what I could do some EDA on for now.
Sounds good. Cool. So that's everyone who's posted in the Slack. Oh, Gurjeet, I saw an article. I'll have to dig it up for you guys. It was an article that was like talking about using data to predict what'll happen to the housing market if we enter a recession due to Corona. So that might be interesting to you guys. If I forget to send that to you, make sure you remind me. All right, who's on the call that we haven't talked to yet? Carol. Carol, who's your partner? Is it Hareem? I think so, right? Carol or Hareem, are you guys out there?
Hello.
Hey, what's up?
Oh, okay, hi. So we first had a data set. One sec. I'm hearing echoes.
Uh-huh. If you put headphones in, that should help.
Hello?
Yep.
Okay. So we had a data set on Kaggle for COVID-19, studying the amount of cases within the United States, but it ended up not really updating well, so we switched to a more reliable source. So now we're using a data set from the New York Times, and we are hoping to create a visualization of the flattening of the curve over time. And that's our primary goal. And then after that, we'd like to create secondary visualizations studying the mortality rates based on age and incubation periods compared to other viruses. So that's
Sounds
our
great.
plan.
Do you have a notebook or anything like that where you've loaded the data in?
Yes.
Cool. If it's in a GitHub, drop us that link. If it's just a file, you can email it to both of us, but that sounds great. Thanks for the update. All right, heard from these guys. Marina, I don't think we've heard from you, have we?
Yeah, hi.
Hi.
So my partner is Anastasia. I don't think she's on the call right now.
Yeah, it doesn't look like it. That's okay.
Okay, so we kind of decided to choose Quick Draw dataset. It's a Google Online game where you can draw image and the machine guesses what it is, and they kind of collect all the images from people. So we decided to try to do this, and the first step we want to achieve is that we have like a window and the user just draws something and the machine guesses what it is based on the data set. And we want to use convolutional neural network. That's what we're trying to learn right now. We don't have much progress. We don't have GitHub link. But what I've done so far is just I parsed some data because it's a huge data set. It's just unbelievably huge data set. And I just managed to read it and store somehow. That's all I've done so far.
That's a pretty big challenge on that data set. Sorry, Carlos, what were you saying?
Yeah, if you're planning to use CNN, you should use Google Colab to train the model.
I was going to say the exact same thing.
Because if not, you're going to spend days just...
Yeah, no, I chose, like, they have like 400 different types of images, and for each type of image, they have like 6,000. It's just unbelievable number. But I chose like a part of it, so I'm working on just a part of it right now. But yes, I will use Google Collaborate to train the model later.
Okay.
That's good. Yeah, we'll get you set up in Colab and show you how to do that. I think, Jorge, I think you're the only one left on the call we haven't heard from.
Julio, right?
Julio was someone's partner, I thought.
Shizoda.
Okay.
Yeah, Julio's with Shizoda. Jorge, are you out there?
Yeah, can you hear me?
Yep.
So the data set I've decided to work on is it basically has the top 100 songs for the past 20 years. And I was playing around with it recently, and I'm trying to like, probably the end goal that I have in my mind is just trying to see like the most successful artists based on the top songs that they've had. And the data set is it's big, but it doesn't have that many columns. It has just the name of the song, the position, and the artist, as well as like each country's like ranking basically. So
Cool.
that's the thing I've set my mind on.
So I think I'll look around for you, but I know that Spotify has really cool data on like characteristics of a song. So it's like the tempo, and there's like stuff about like how upbeat it is basically. So let me see if I can find that, because that would be a cool thing to join on and look at like how those characteristics influence how successful a song is. But that sounds good. Do you have a partner, Jorge, or were you working by yourself?
No, I'm working by myself.
Cool. All right. Thanks for those updates, everybody. Fun to hear what you're up to. So we're going to split up into groups now. Did any of those projects sound like something you would be able to be extra good at helping, Carlos, or should I just split us up kind of randomly? I can just split us up. I just wanted to check. All right, so let's do Shizoda and Julio. You guys can stay on the call with Carlos. Wow, I can't read my own handwriting. Tyron, go ahead and stay on the call with Carlos. Carol and Hareem, you guys can stay on the call with Carlos. So that's 3 groups, and then one more. Maybe Huaylin. Who was Huaylin's partner? Sorry. Tanya, right? Yeah. Huaylin and Tanya, why don't you guys stay on the call with Carlos too? So that means I'm going to post a link in the Slack here in 1 second. And Sar and Nassan, Gurjit and Meldon, Marina and Anastasia, and Jorge, you're going to join the Hangouts link that I post in the Slack. And so real quick before we hop off, like I said, we're not going to come back together at the end because that would be too tricky to navigate. So after we're done in our individual calls, that'll be it for the class. So real quick before we split up, any questions that people have about the class in general? Or any announcements that we have, Carlos? I'm trying to think if there's anything important we should say as we're all one big group.
So next week we're going to cover okay. You can get a heads up.
I think we had talked about doing natural language processing, but it seems like more people are doing image recognition than NLP. So maybe we should do image recognition next week and do NLP at the end of class so that the image recognition students can get a little bit of background on how to do CNNs and stuff. Does that make sense?
And yeah, I guess like we should start first doing regression and classification using deep learning, and then move to
that makes sense. A more general deep learning. Cool. Let's do that. So next week we'll do deep learning, and then we'll try to get to the image stuff as fast as we can so that you guys who are doing images can see how it's done. But you guys doing images, we can also just show you before we get to it in class, and that'll be okay too. Cool. So next week we'll start deep learning. What'd you say?
Also, CNN is kind of complex. Understanding.
Yeah. I was honestly just thinking we could just do like how to do a transfer, how to train a transfer model without even getting into the theory, but that's a discussion for another day. Cool. So we'll see what we do next week. Obviously, we're still talking about it, but it'll be something about machine learning and CoLab. Sweet. I'm going to go ahead and post this meetup link. Give me a second while we're getting set up. All right. It's in the Slack, and I'm going to add, so I said SAR Nassan. No, Nassan's not on the call. Gurjeet. All right, cool. All right. Bye, everybody that's on the Zoom call. Oh, wait, I have to assign a host before I leave. How do I assign? All right, Carlos, you're the host now. Congratulations.
Guys, stay safe. All right. So, guys, do you have any questions? Like, do you want to go over the notebook you started working on? Come on, guys.
Question: do you have any other sources where you use for like image classification? Because what I've done so far, I've been reviewing the TensorFlow example on the clothing data set they have.
Uh-huh.
And then I came across like another method. Instead of building my own neural network, I could do like transfer learning, which you mentioned.
Yeah.
That use already people who already build these models, and then I just feed my model into like the same model, but only change like I think the last layer, something like
Yeah.
that happens.
Basically, what you do is you only change the top, but so there is a little trick for that, and is that you have to make at least the last 2 or 3 layers trainable, and while the first layers they're not supposed to be trainable because the models are already trained.
Mhm.
But yeah, I can give you let me see if I find some links to it. Okay, Keras model. You, you, which model are you using? Teron.
I don't really have a model right now. I'm still like doing some research.
Okay. So there are a few models that like every year they have the ImageNet competition. One of the most famous models is called Inception. It was it's from Google. Can look at let me look Inception. Let me see in the link. So one of the actually let me look for let's see this. You guys have any questions? Like, do you want to go over the notebook? I don't know, like maybe help you with some of the code to do some EDA.
Do you have any animation examples?
For what?
Like just an example of how to get certain animations?
You mean like in a graph?
Yeah.
I would say Bucket is pretty good. Let me see a link. Hold on, let me go to YouTube. So Bucket is it's like Matplotlib. Which one is good? So here's the link to the bulkhead documentation. You can check the tutorials.
Okay, thank you.
You're welcome.
Have you done like a lot of like geographical mapping for data? Because I've used GeoPandas and Folium. Do you
Yeah.
know what is better to use, or like what is used a lot more?
It all depends.
It's
So
been a lot buggy for me in like Folium. Like it's working sometimes, and then sometimes like it's
okay.
not feeling correctly when you're zooming out and everything. But it does look really nice.
Yeah, I would say because I did a project and I was using base map, which is from Matplotlib, but that's different. But yeah, I think Falling works pretty well. You can you can also use the Google API from the Python notebook. There's also another let me send you this one. So I just learned about this is called ArcView.
What was that again?
Hold on, let me send it to you. Because I'm looking for the file link where I found it. This is more for spatial data, like as you were saying, like you were using GeoPandas, and I would say GeoPandas is pretty good, but there are some other libraries that are actually specialized for. Hold on. Let me see. Okay, I found it. So here's the link. So using the ArcGIS API, you can even build some real-time maps. Like if you're getting real-time data, and yeah.
Oh, that's cool. Because I built another notebook where I don't know if you saw in the Slack, I was working on the coronavirus cases, trying to download the data directly from GitHub.
Uh-huh.
Yeah, so I'm getting like pulling all the because they update it daily. Like every day they have a new CSV file with the day and the cases and locations.
Mhm.
I was trying to find a way to create a function to grab the data and then filter it and find the things and make a data frame because I
Yeah.
have really weird.
I mean, the usually the way that I do it like is I build web scraper. You know what that is?
Yeah, I also did a web scraper code too. It's
Uh-huh.
pretty long, but like that one, the other way I did it, I can show you my web scripting code too. But the
Okay.
other way, I just downloaded the master zip file and then it pulled all the CSV files, and then it concatenate all the CSV files into the data frame.
Oh, you're good, man. That's you know how to code that in data engineering?
Yeah, I did some.
That's ETL.
I did the web scraping one I did.
Mhm.
Was I pull the data to like it checks for data based on when it was updated, gets all the CSV files, and then it makes a dictionary of like all the data. And I have to filter in such a way like I could get the keys that are unique, so I don't have like duplicates. So I was still messing with that, make sure that the data doesn't like duplicate certain places. If I pull and then it replicates again.
Do you set up a routine for that?
Excuse me?
Do you have a routine? Like it is automated, it runs by itself, or you have to run it?
You have to run the code. Like you just call it's a function though.
Yeah.
I've been trying to build a lot of functions, so like I don't have to write everything every time I work on different projects. So I could reuse those codes that I made.
Okay, that's good.
Yeah, I spent a lot of time like trying to make the codes reusable.
It's a smart move. But yeah, I mean, if you want to automate it, you can set up a cron job, and what it does, it calls the function itself, and just forget about it.
So like predict rent prices. What kind of features would we need?
To predict rent prices.
Rent. Yeah.
All right, so let me give you an example. Do you guys remember when we did the Boston housing data set?
Right. Yeah.
So like you have to, I would say, it has the variables of the crime rate, the size of the house, yeah, even the size of the land. If you how many rooms he has, how many bathrooms, the color of the house, and how many doors. What else? The neighborhood.
I did web scraping for Zillow and I only got prices, bedrooms, bathrooms, and the square footage for some, not all of them. You think that's enough for like linear regression?
Oh, how many columns you have in total?
I don't know, 4, maybe 5, with the address.
With the address?
Yeah.
Okay. I would say maybe some of the columns are categorical, meaning that using that column can create more columns. Do you remember when we did the one hot encoding? That basically you set up a one for the value when you make a column, and if it is not, it is a 0. It's like mostly like an indicator, basically.
Okay.
I mean, it all depends what you have. Can you show it to me, or do you want to show it to me?
Sure, yeah. I think I have a link. Wait.
Okay. Does anyone else have a question? Come on, guys. Okay. This is the web scraper, yeah.
Okay, yeah, that's a web scraper. And then This is pretty much what it comes out. So I have the price, the address, which is super long, and bedrooms, but I don't know the square footage for some of them. A lot of them just have this.
Yeah. So you see, you have the price ad. Well, you don't. The address does. What you can do with the address, you can maybe group something, but like let's say, for example, by county.
Okay, like the zip code too. I think some. Oh,
Yeah.
yeah, zip code.
Take the zip code, and you can group it by county. So
Okay,
that,
cool.
okay.
Would that be enough for like linear
Um,
regression, or still too little?
I don't know. Maybe, man. I would say like if you want to go hardcore, or maybe you can also take the image and extract the color
Oh,
of the.
right, yeah. Okay, cool, yeah. Thank you.
All right. Anybody else? Harim.
Hi. Can you hear me?
Yes.
Oh, we were just me and Carl were on a separate chat, so we're making branches right now.
Okay.
Yeah, so we just uploaded the new New York Times data set.
Uh-huh.
So we haven't conducted any initial analysis yet, but we're trying to find out how to do it without having any conflicts with each other.
Okay. Oh, so what you can do, you can create branches.
Yeah, we're doing that right now because while you were just talking.
Yeah, you told me. True.
Yeah. But we're also making we had our repository private, but then because you were looking at other people's stuff, so I'm like, we should make it public.
Okay.
Yeah. I mean, it's nothing big yet. Yeah. We're working on it.
Okay. That's good to know. Then.
Okay, thank you.
But what do you actually want to analyze from the data set? Like, what is your main goal?
Our main goal is to figure out, well, we know the curve is kind of flattening in real life, but we want to see if we can make a visualization of it. So when someone looks back at it in another 10 years, they'll see what the data was like and how the curve flattened over time.
Mm-hmm.
So I remember how in the beginning of the semester, how you showed us one of your visualizations that you did and how the graph changed over time.
Okay. Oh yeah. But that was there's no Python in it. That was using JavaScript.
Yeah, but it was interesting to see how that worked out. So in my head, it's kind of similar to that.
So let me send you this link. So maybe you find something interesting.
Okay.
So they have data about coronavirus, and basically it gets updated sometimes every minute.
Oh wow. I think that's good. Thank you.
Right. So who else? Okay. Soda.
Yeah, I'm just messaging Julia right now, and we're talking about rent prices. So
Okay.
yeah, we're working on our project.
Okay, cool. Questions? Come on, guys. Let me check. Does anyone have a question about today's lecture? No questions at all? Do you guys like it?
Yeah, it's cool. I've never done PCA before.
Okay.
This is something new that I did.
What do you think about it?
I didn't know you could actually do that, like have a combination of like where it takes a combination of all the features and you can make them into two parts and then you can see a visual of it.
Okay.
Because I noticed that like a big problem like having high dimensions.
Yeah.
It's hard to visualize to know which features are more important or like which ones to use.
So let me ask you something. What else do you think PCA can be used for?
Other than reducing dimensionality?
I mean, like one real life example. Using the, like reducing the dimensionality, but for a real life example.
I guess like going for the like the pricing homes, pricing for homes. You know,
Okay.
there's like different contribution to that, like you collect all sorts of data, like the community, the crime rate, the location, the income, maybe like the nearest like precinct or the nearest like stores and all that.
But I'm sorry, but let's say outside of machine learning, like you don't want to do any machine learning. You're just receiving data.
Just receiving.
Yeah.
Sure.
In that case, I would say it's good to save a space. Like if you're saving data and that is constantly coming in, and you don't know what it is, just get how many components you want. Let's say if you want only like 5 components, and then you can save it for later on.
Wait, so you can use as a filter, like
Yeah.
as you're feeding data into it, you'll pick like 5 important ones and save.
Yeah, and then later on you can do the inverse transform. If you have the PCA object safe.
Mm-hmm. Gotta read more about that.
Mm-hmm. Yeah, that was a good word. It's like a filter.
What's really cool is the pie carrot thing I came across. The people who build that library that I shared. Like you can see it does like almost everything for you. It's like a wrapper for all of the scikit-learn and like other libraries. And it shows you like it runs like all these machine learning algorithms that show you the best ones, and you can even check like the best parameters for certain ones too.
Yeah, I think it's very useful. I think I'm gonna give it a try and see how it works. But yeah, man, it seems like it saves you time just building everything from scratch. And thank you for sharing that.
Yeah, no problem.
Quick question: have you guys ever heard about Deep Dream?
I heard of deep fakes, not deep dreams.
I'll send you a video now. It's just so these people they use convolutional neural networks to generate fake images. So they make movies out of it. Let me see this one as well.
Oh yeah, I have a question. You said you did the data science masters at CCNY.
Yeah.
Or is it the CCNY one or the Graduate Center? Because I know there's two.
Yeah, CCNY. Steve was he went to the Graduate Center, but yeah, I'm going to CCNY now.
How do you like the CCNY one? Because I'm thinking of doing it next semester.
I
It's
mean,
a lot more hands-on, or like how is it?
yeah, it's, I mean, like what I've noticed so far, because this year, I mean, last semester and this semester, we're taking classes together, and yeah, like the classes we take are more hands-on than theory. Um,
But are you getting like the theory, like it's making sense and like they're explaining it well?
yeah, because basically, so here's the thing: the math used for machine learning is not that complicated, as long as you understand linear algebra and calc 3.
Because I have a professor right now, like I'm taking the intro to data science in the math department, and he goes in depth into like the linear algebra, and then he shows us the transform into using like QR decomposition.
That's too much theory, man.
Yeah, he goes in a lot, and he likes the theory, so we go in like really in depth using like Grand Schmidt and like deriving like all these different ways how to do it. But it's all the same thing, like using, I believe for linear regression, like if your features are the same size as the number of data points in data set, like you get a perfect model. It's always like 100% R squared and no errors. And it's like X transform X inverse X transpose. Like that's basically the linear algebra part, how to get your prediction.
That's what a linear regression is.
Yeah.
So basically, you get the weights the inverse transform. But yeah, man, the math is not that complicated. But I would say it's better to go hands-on, because that way you learn more algorithms and yeah, this is about practice and there's one thing. So this is the idea. You know what data science is itself?
It's just statistics. So there's statistical learning.
It is. So this is the point. Supposedly, a data scientist knows more statistics than a computer scientist, but knows more he has more computer skills than a statistician. So the idea is that you use the packages that other people have built to solve statistics problems using the computer. So I would say knowing the theory is good, because it allows you to understand what the model is actually doing. But I'm sorry.
Yeah, it's kind of torture. We've done like we're using R for the class.
Yeah.
We're building all the models from scratch and then doing like a bunch of statistical analysis on it.
I mean, in a sense, like if you're building the model from scratch, I would say in a sense it's good.
Yeah.
Because that allows you to understand how the model actually works, how the actual algorithm works. But yeah, man, it's just, I would say it's hard, like getting jammed with.
Yeah, it's pretty cool though. Even though it takes a while to do, it's still like I understand like what's going on in each of the models.
Yeah. You take a probability before?
Yeah, I took all probability. I took all the stats class and all the calc classes.
Oh, you'd be good then, man. You are in a good shape, and especially now you're taking you're doing this class.
Yeah,
I would say this class you're gonna have a huge advantage compared to other students. All right, so for my intro class, the introductory to data science is basically we did the same thing we're doing in this class, but a little bit more in depth. Do you apply to the program already?
No, I didn't apply. I was thinking about applying, but it was like too late. I have a friend that's gonna start it in the fall, so I was waiting on him to tell me how it is, and then I'll apply and see.
Okay, okay. I see. Yeah, man, I like the classes. Are you planning to go like into data science or software engineering?
Still undecisive. I like either or.
Uh-huh.
So like whatever comes my way. But I go for my master's. I want to do data science.
Okay. I mean, you can try data engineering, which is basically a mix of the two.
There are not a lot of people like the data engineering. They're just like in between.
Yeah, I mean, I like both, man. Actually, I prefer data engineering than it's more fun. Okay, guys, any questions? Come on. Carol.
Would CNN be like the most simplest model to do image classification on, or other more simple models?
To do what?
Image classification.
I would say CNN is the preferred model for image classification. Because, all right, so let me see how I phrase it. You can do image classification using deep learning, like just straight classification. But what happens is that, like, let's say if you see my face here, right, in the camera.
Yeah.
You see the square of the box, right?
Mm-hmm.
So if you use just deep learning, what they call like a dense model, it's not going to be able to spot things in different places. Let's say, for example, if you want to spot, like, let's say this letter here, the letter C,
Mm-hmm.
right? If you use CompNet, it doesn't matter where the position of the picture. Like, it can be here, you can move it, and that is called. In fact, like, if you want to increase the data you have, like the images you have, you can use data augmentation. So what it does is that it take an image, it stretches the image, and those things like that. So the classification itself doesn't change. So the whole point is that CNN are capable of detecting things no matter the position of the picture.
Okay.
You see why CNN is good?
Yeah.
Like the edge of a corner, for example, or so. Yeah, man. Like, I've been taking, like this semester, I'm taking deep learning, and that is good, man. That there's a lot to learn, and it's very useful.
Yeah, I got started because of over the summer, I had a couple of my friends wanted to build an autonomous RC car. So we
Okay.
just learning, and then we looking into ways how to collect the data. So I had an RC car. We took it apart. But a couple of my friends are electrical engineering from CCNY
Mm-hmm.
and from upstate in Syracuse, and they wanted to use like a bunch of electrical engineering components, like a L298 chip, where it, like, controls like the.
I have no idea.
Yeah, like we actually spend more time building the car from scratch, or is controlling using different chipsets.
Yeah.
Like different microcontrollers, and then we went on from using Arduino, where it's just one script. So Arduino, you just going to run one script at a time. And then we transferred back to Raspberry Pi. We used Python, and we made like a remote controller with Python. was able to drive the car around.
That's pretty cool, man.
But that's the part we stopped. We were trying to collect like the throttling speed and like the direction it was moving, like the different angles. And then we use it to like train it to go in a certain path. But we got stuck like where we want to position the car, like inside or outside, because when you collect images, like there's different like stuff that could go wrong, like the lighting, like what the path that it's following.
Mm-hmm.
So we were thinking like indoor, just have like white lines, like have white tape. We had to find a location where the car could just track inside the white tape and just following it and drive by itself.
I think this is a smart move.
Yeah, I think we're starting it back up this summer, hopefully.
Let me know when you guys are ready, so I want to see it, man. You know, I used to be from Grove as well.
That's cool. Oh, it's really cool to look into. It's called Donkey Car. They have like competitions like all over the U.S. where people build their own autonomous cars and then they go race them.
Okay.
So, yeah.
Thank you.
That's where I got like the idea from.
Because I know like the chemical engineering department, they have a competition every year. I mean, that's the Society of Chemical Engineers, and what they do is that you have to build a battery for the car. So it's similar to what you have here. But in the competition, the idea is that you need to determine the amount of every component of the recipe for the battery, so the car reaches like 100 yards. So it has to stop exactly in a line. If you go beyond the line or if you far back,
that's from a club at CCNY?
Yeah.
What's it called?
The Chemi Club.
Oh, okay. Yeah,
no, man, sorry, online. It's called AICHE. That's the name of the club. Let me grab it. Yeah, that's the name. Are you into robotics or?
Kinda. Like my end goal is like working on like AI stuff. So like I'm doing research into like this different like autonomous like driving and autonomous like Alexa AI, like Alexa or like Siri.
I think you could be a good fit, man, for CCNY, because I know this professor. He's also one of the directors of the program.
I was at CCNY at one point. I didn't like it.
Oh yeah.
I left CCNY and went to Queens to finish my CCNY started as electrical engineering, and I didn't like it, and I didn't like how far I had to travel, and then I transferred to Queens College and did CS there.
Okay.
Yeah, so I did like a turn from electrical engineering to CS. I like CS now.
You like CS? Me too, man. I actually did my bachelor's in chemical engineering, but if I would have to start again, I would do CS instead. So you like coding?
Yeah, it's really fun. And I enjoy writing scripts in Python too. It's my favorite. I picked it up for myself actually, because in Queens they only teach you is Java.
Okay. I mean, that's good, man. That means you are a self-taught person, which is a good skill. All right, guys. Any questions? Come on. This is your last chance. You guys have any questions about the lecture from, was what, 2 weeks ago? The regression lecture, or from classification? Any questions about data science at all? Yeah, Julio.
I was gonna say, I'm taking a machine learning class, but he's not using the libraries. He's just doing it from scratch.
Okay.
So it gets really confusing. What math do you think is like the
math?
most they need?
Linear algebra?
Linear algebra?
Yeah.
Yeah, I never took that.
Yeah, man.
You know what you should look into? I think MIT has a really good linear algebra course, like the best. I forgot the guy's name. I could link you just now. A lot of people like his I think it's like Gilbert or something like that. He's like really
Awesome, yeah. Great.
I mean, what language are you using? Python or
Python, but honestly, it's just writing equations. Like today we were looking at the kernel thing, and it was just like a long equation.
I hate that, man.
Yeah.
Like that's what I was saying. Like I like things more applied.
That's how my math data science class is too. It's just loaded with equations.
Yeah, it should be like a math class instead of machine learning.
I mean, if it is math or data science, that's is understandable, or even in statistics. But if it is something more like data sciencey, like say for example, this class, introduction or visualization or data engineering, big data, is something that you expect that. I mean, it must be hands-on because it's coding, and I always say that coding, and no matter which field, is something that you learn by doing, not by just pretending to do something.
Yeah, for the linear algebra, it's like Gilbert Strang. His textbook is really good, and his videos are really good.
Oh yeah, I'll take a look at it. Maybe try to take linear algebra next semester or so.
Yeah, if you take that course, you'll know more than like the class will teach you.
You like calculus?
I took calculus too. That's it.
All right, so linear algebra is just it's a different math, man. It's completely different. You have never seen something like it. But don't get scared. Don't get scared. It's easy.
Yeah, we got like the matrix and stuff. Yeah, like completely different.
Yeah. But as I said, man, it's another word. But it's easier than calculus, or it's more intuitive. That's the word. So I think this is it, right?
Thanks for all the help.
Cool. Yeah, thank you.
So guys, before you leave the meeting, don't forget, Tuesday I have my office hours from 7 to 10. If you want to pop by and have questions about the project. So yeah, stay safe, everyone. Stay healthy.
Bye bye. Have a great weekend, guys.
All right, you too.